So should I just?
Yeah. So our speaker today will be Shirshendu Ganguly, who will speak about the environment seen from infinite geodesics in Liouville quantum gravity. So Shirshendu, go ahead.
Yeah, thanks a lot, Evan. Thanks for the invitation. Yeah, so we'll talk about some recent work that I did with Basu, who's at ICTS Bangalore, and Manan Bhatia, who is a studying grad student at MIT. And so actually, so this is a topic that I've actually not worked at all in the past. And so many of the audience members actually know much more about this than I do. But the broad question that I'll be talking about is something that has also seen some activity in other models of planar metrics, which I'm more familiar with. And so some of the goal was to sort of import some of those ideas in this setting. And feel free to jump in with sort of comments or suggestions. Yeah, so I want to keep this more interactive, and also stop me if something is unclear. Okay, so just to get started with the sort of broad sort of goal and where the question comes from. So let's start with a very basic model of first passage percolation on Z2. So this is sort of in some sense the first canonical sort of random metric space that people sort of considered. And so the description is very simple. So you simply, let's say, have Z2 to begin with, and on every edge, let's say you put an ID, a non-negative random variable XC. So let's see how, yeah. So every edge here E will have a IID random variable XC attached to that, and this and so you should think of this as the new length of this edge, and so this induces a random distortion of Z2. And let's say the associated graph metric will be denoted by T. So Txy will be the new distance between X and Y in this new weighted version of Z2. And so geodesics are the shortest paths in this metric. So between X and Y, so we'll denote it by gamma XY. And so there might be multiple such geodesics, but it turns out that for Z2, if the weight distribution XC is continuous, then because you can show that almost surely no two paths will have the same weight, you can show that there's a unique geodesic. So that's going to be an important object, of course. And several results are known. So one particular thing that should be sort of interesting to record is the symptotic speed. So let's say you fix any V in R2, and now let's say you look at the distance in this random metric space between the origin and n times V. So you can think of V as a unit vector maybe. And so look at this sort of growing sequence of vectors n times V, and you can sort of round it to make it an integer point. And look at the passage, the distance between 0 and nv, and then let's say you scale it by n. So this quantity grows linearly in n, and you divide by n, and so it turns out that this thing will converge to some number mu v, which is a function of the direction v in which you were growing. So this sequence of random variables will converge to mu v in probability. And there's this famous shape theorem by Cox and Duret, and later sort of strengthened by Keston, who proves a version of this result for all V simultaneously in some sense, as long as, let's say, V is on the unit sphere. Okay, so every direction has some speed. Okay, so this tells you that the length of the geodesic between 0 and any direction has some asymptotic speed, and so geodesics are length minimizing paths because they're the shortest paths in this metric space. So which means that you have all these sort of edges with random weights, and so the geodesic will tend to pass through the ones that have atypically low values because it's trying to minimize its length. And so it's an important question to sort of understand how does the environment behave if you now look at it from the geodesic. So because the geodesic has this tendency to pass through low values, so if you sit on the geodesic and you look at the environment from that vantage point, so then it sort of will be different from if it were just rooted at the origin. And so somehow the sort of broad goal is to understand what the disparity is. And so there are multiple ways to maybe quantify that. So one sort of natural way is to look at empirical measures. So let's say you have this geodesic gamma or gamma n, which goes from 0 to n E1. E1 is this canonical vector in the x direction. So so you have all these edges along this path. So let's say, and you have all this edge weights on each of these edges. So XC is recall that XC was the edge weight associated to the edge E. So now I can put just delta mass on all the edges along this path and just look at the empirical measure where you put 1 over the length of gamma. So this denotes the number of edges on the path gamma. So, and this sum has exactly this many edges in the sum. So you put delta mass on all the edge weights that you see along the path and then properly normalize it to make it into a probability measure. Now you see that this passage time or the distance between 0 and NE1 is exactly some sort of version of the expectation of this probability measure, right? So this probability measure puts sort of up to this constant Dirac masses at all the edge weights, and the passage time or the distance is simply the sum of the edge weights. So it's up to this prefactor, which is the length of the path, the expectation of this probability measure. And also it's not hard to see that because the length of because this path is length minimizing, the passage time will have expectation, or the speed is going to be smaller than the expectation of an individual edge, right? Because clearly this thing itself is a candidate path. So you go from 0 to NE1, you just take the straight line, and each of these edges are IID. So the length here would roughly be, by law of large numbers, n times expectation of XC for any edge, because these are all IID. And the geodesic itself is actually the best path. So it's going to do actually, it's sort of not hard to show that under very natural conditions, the length of this path is going to be macroscopically smaller than this candidate. So which then sort of implies that the expectation of this empirical measure is going to be smaller than the expectation of the starting distribution. Any questions so far? Okay. And so towards sort of understanding what this measure looks like, so Chris Hoffman sort of posed the following question, and particularly it has been recorded in this sort of meeting that happened at AIM in 2015, is that does this sequence of measures as n go to infinity? So recall that, sorry. Sorry, something is happening. Okay, just a sec. Yeah, so this is empirical measure, and you have a sequence of empirical measures as n goes to infinity. And what Hoffman asked was, as n goes to infinity, does this sequence of measures converge weakly to some probability measure? So there are some sort of conditions that you need, because this question, as written, does not have a so it's not quite sort of, the answer is not quite yes, because you see that if the random variables have some positive mass at 0, then the geodesic will typically have occasions where it will pass through boxes which have all zeros in them. And so then no matter what you do inside, it's not going to change your length. So if the red path is geodesic, and so is this new path which does something very strange inside this box of all zeros, because it's not going to affect its length at all, but it changes the total number of edges that the path has. And the way we formulated the question about empirical measure, the Dirac mass somehow on each of the edge weights, sort of the non-zero edge weights stay the same, but the zeros can really increase, and then that can also change the length, total number of edges that the path sort of passes through. So we have to reformulate this a little bit to sort of have a situation where the answer to this question is yes. And this was actually somehow formulated and answered in a sort of very interesting paper by Eric Bates, who proved that the answer to this question is yes for any generic distribution. So some of the arguments were very abstract and relied on convex analysis, ergodicity, etc. So it does not provide any sort of explicit example of the edge weight distribution for which the answer to Hoffman's question is yes, but it says that, oh, if you look at the class of all distributions, it's true for most of the distributions in some sort of density sense. Okay, so this was a paper that came out last year. And then shortly after, in a separate paper, Zhang, Lam, and Shen, they did not prove existence of sort of a weak limit for the sequence of empirical measures, but they showed that. So they obtained some tail estimates. So they showed that if the starting distribution XC, the edge weight distribution, has, let's say, any finite positive moment, then any weak limit point of this sequence of empirical measures has all moments. And that sort of is not surprising, because somehow it sort of passes through all these sort of atypically low weights, so it has much lighter tail. But this paper does not quite prove existence of limits as well. So that was what happened last year around FPP on Z2. And so there is this parallel sort of setup where somehow you have these problems which are inspired from FPP, but the models are such that you have some algebraic connections, and that actually makes your life much simpler. And you can use those integrable inputs to really understand this at a much more refined scale. And so I'll just sort of briefly mention this. So the exactly solvable setting, there are sort of multiple models, but one thing that sort of is easy to describe is it's basically like FPP, but there are some key differences. So instead of looking at all paths, now let's say look at oriented paths. So the vortex, so instead of having weights on edges, now each vortex is equipped with a random weight. And now instead of looking at all paths, you look at oriented paths, in this particular picture, paths that only go northwest or northeast. And let's say all the edge vortex weights are IID exponential 1. And also in FPP, you look at, FPP is a random metric space. So you look at 2 points and you look at the path with the shortest length. So in this setup, you actually look at the path with the longest length. So you look at, let's say you fix 2 points upstairs and downstairs. You look at all oriented paths. For each path, you sum up the vortex weights along the path. And you now look at the path which maximizes the sort of sum of the weights along the path. And you can ask the same question. So this is again sort of by abusive notation, even the geodesics are typically used to describe shortest paths. Even in this literature, this longest weight maximizing paths are also known as geodesics. And you can look at this geodesic, and let's say you take some random point on this geodesic, and you can try to understand what the measure looks like nearby. And in the paper that came out this year, James Martin, Alan Sly, and Lingfu Zhang gave a very explicit description of this local environment using connections to particle systems that this sort of integrable model admits. Okay, so there's been quite a lot of activity both in FPP and in, this is known as last passage percolation because it's sort of maximizing paths instead of minimizing paths. So it's known as LPP. And subsequently, sort of Davon, Sarkar, and Virag also proved a similar result, but for the directal landscape, which is the conjectural scaling limit of all this last passage percolation model. So the slide, the previous slide described this lattice model, which had exponential weights on the vortices, but then there is a way to actually limit of the entire metric type object, and what one gets is what is known as the directal landscape. And it turns out that a similar result is true, of course, in the scaling limit, and this was shown by this group. And so the broad sort of kind of things that go into the proof is, and so why do you expect sort of this kind of limits to exist, is because the noise, sort of IID exponentials, or even in the directal landscape, the noise that drives the sort of metric spaces are spatially independent. So there is a spatial independence in the underlying noise. And the key property that gets used in all of these arguments is a phenomenon known as geodesic coalescence or confluence, as it is known in the LQG literature. So any questions so far? Okay, so I'll quickly describe what coalescence or confluence means for people who are not familiar with it. So and so this is sort of a key sort of phenomenon and a key concept that gets used a lot in understanding metric properties in FPP, LPP, and LQG, is that because geodesics are path minimizing, are weight minimizing paths, if you, let's say, take 4 points and 2 of them are here and 2 of them are here, if you take the shortest path going from this point to this point and this point to this point, they will typically tend to meet, merge, and continue their journey together, and then eventually sort of separate. And that's because they're both trying to get to the sort of random part of the region where the weights are atypically low. So you have all this sort of random noise that is driving your metric, and then you have some atypically low weight somewhere nearby. And so no matter where you start from, the paths will sort of tend to move to that direction, and hence will sort of merge. Okay, so that's sort of the phenomenon of coalescence, which is completely absent in Euclidean geometry, where geodesics are straight lines. So either two geodesics do not meet at all, or if they meet at a single point. Okay, so given this sort of background about this sort of question of the environment seen from the geodesic and sort of the activity around this in FPP on Z2 and LPP, it's sort of natural to ask whether one can sort of develop a similar program in the setting of Liouville quantum gravity. So, okay, of course, most of you are familiar with the basic setup, but just let me go through it quickly for people who might not be. So this is a family of models of random surfaces and it was introduced in the 80s by physicists, and it has been studied extensively since then. And it admits various connections to various discrete statistical mechanics objects, and in particular to things like random planar maps. Okay, so defining it is a challenge, and so I'll just do it I'll sort of basically describe the basic ingredients informally. So the driving noise is the Gaussian free field, the whole plane version of it. So I won't go too much into how actually precisely define this object, but it's a centered Gaussian process H with a particular covariance function. It looks like the Green's function on Z2 or on R2, but one has to be a bit careful to make sense of things, and so you have to normalize. And it turns out that the explicit covariance function is this formula. So you don't have to look too closely at that, but you see that the log appears, which is not surprising because that's what the Green function is on R2. And you have this distance between z minus w, and then you have something in the numerator, and this might look a bit strange, and the reason is something that will become a bit clearer in the next slide. Okay, so it's a centered Gaussian process on the whole plane. However, it is not a function because it's not smooth, so it's very rough, and so you can only make sense of it as a distribution or a generalized function. So it only sort of gives you nice objects when you hit it against sort of smooth test functions. And so the precise form of this covariance that I sort of presented in the last slide is because so to make sense of this sort of whole plane GFF, you have to normalize in a particular, you have to normalize in some way, and the sort of convention that we will follow in this talk is that you sort of simply make the average of this Gaussian process on the unit circle 0. So even though it's not a function, you can actually make sense of the average on circles, and you sort of pin the Gaussian process to have this 0 circle average, and that's what exactly gives you the covariance function that I presented. Okay, so that's going to be so instead of this sort of white noise or ID spacetime noise that drove the initial models that I was describing, like FPP and LPP, here the underlying noise is going to be this canonical log-correlated Gaussian process. And so the LQG metric can be interpreted as a sort of random Riemannian metric with tensor given by exponential of 2 power. Yeah, sorry, my iPad behaves funny sometimes. Yeah, so the LQG metric can be, so given this Gaussian free field H, the LQG metric can be interpreted as this Riemannian metric tensor given by e power 2 times xih, and with the and so this is a prefactor that gets multiplied to the usual Euclidean metric tensor. And so what is this xi? So gamma is going to be a parameter. So the LQG, I'm like, so for us, gamma is going to be a parameter between 0 and 2. And so this is a family of Riemannian metrics in some sense, and this number xi is going to be gamma over some quantity which is also a function of gamma called d gamma, and you can compute d gamma in various ways, and it turns out that d gamma will, so once you define this properly, d gamma will also turn out to be the Husserl dimension of this metric space. Okay, so you have the Gaussian free field, you essentially exponentiate that with some gamma dependent prefactor, and that's going to be the distortion factor on top of the usual Euclidean metric. Okay, however, this is all super imprecise, and it's actually a sort of really hard problem to make sense of this precisely, and what one does, a natural approach is to sort of mollify or regularize the underlying Gaussian process. However, so everything becomes nice if you smoothen the underlying Gaussian process, but then you have to show that as the smoothing becomes smaller and smaller, there is in some sense a limiting object that you get, and this was sort of open for a while, and it was overcome through a long list of works, and so because I've listed some of them, I don't think I've missed any, but maybe feel free to sort of correct me if I'm wrong. So there was this important paper by Ding, Dunlop, Dubeda, and Falconet. Ding, Falconet, Is that true? Yeah, or maybe Dubeda, Falconet, Gwen, Pfeiffer, and Shen, and then a list of papers by Gwen and Miller. I think I covered all of them, right? Even you can jump in. Yeah, so this sort of really sort of rigorously constructed what this means to have this sort of random Riemannian metric. And so given this metric space, what we will be interested in are infinite geodesics. And so this was proven in this recent paper of Gwen, Pfeiffer, and Sheffield, that for every z on the complex plane, almost surely there exists an infinite geodesic emanating from z. And so it need not be unique. So this is sort of a cartoon for that. So z is some arbitrary point on the complex plane, and there's going to be some semi-infinite geodesic which goes off to infinity starting from z, and there might be multiple. However, if you fix your z, then almost surely there's going to be a unique geodesic. So let's say if z was the origin, then almost surely in the realization of this metric space, there's going to be a unique semi-infinite geodesic going out from the origin. So sort of going along the same question, so we'll sort of try to understand how does the environment seen from some point on this sort of semi-infinite geodesic look like. Okay. Okay, so so we want to understand, so you have this semi-infinite geodesic and you want to understand how does the environment look like from a typical point on the geodesic. So you want to sort of sample a typical point along the geodesic. And so so we have to make sense of what it means for a typical point. So recall that in this sort of FP or LPP description that I did, so again, the noise was IID in space time. I'm like, it's sort of common to call it space time, where you think of space as one dimension and time as the other dimension. So it's a two-dimensional picture. However, because here in this sort of setting of LQG, the underlying noise is the Gaussian free field, which is log related. So this sort of IID type picture is only sort of true once you rescale things. So this sort of the underlying noise sort of exhibits some IID kind of features, only modular rescaling, and so we have to take that into account. And so to do that, so what we do are a couple things. So one of them is a scale dependent dilation. So suppose you look at some point x on the geodesic. So depending on where x is, you look at the ball that you look at around x will depend on the sort of on how far x is. So ideally we would want to consider a ball of, let's say, radius delta. Delta is some small number. However, if you look at but suppose you are rooted at a point x, then what we actually do is look at a ball centered at x with radius delta times the norm of x. So which means that if you look at y, which is much farther from x, you're going to appropriately sort of look at a larger ball. However, we want to pull everything back into a unit disk to look at objects that live on the unit disk. So you look at this ball centered at x of the right radius, then you scale it to map it to the unit disk, and let's call the scaling map as psi. And so now you look at the field, the underlying field, the Gaussian process H, restricted to this ball. And now you sort of compose it with this sort of scaling map so that now it lives on the unit disk. So you look at this environment here, and now you scale everything to live on the unit disk. And now you sort of do some normalization. So you subtract out the constant so that whatever field you get on this unit disk, the average of it on the boundary of it is 0. Okay, so that's sort of a normalization that we do. So no matter what point on the geodesic you look at the corresponding ball of radius delta times the norm of that point around that point, then I finally scale it to push everything to the unit disk and accordingly scale the local field. Okay, so that's the object that we will be caring about. So H bar x is the local field around x, which now lives on the unit disk and is normalized to have average 0 on the boundary. Okay, any questions? Okay, so that's the object that we'll care about. And then the other thing is, how do we parameterize the geodesic? So the geodesic is this infinite object, and because of this log correlation, somehow the geodesic spends an equal amount of log time per scale. So somehow that makes it natural to sort of look at the geodesic via log parameterization. So this is what I mean by that. So think of this map from the real line to the geodesic, where S maps to gamma of e power s. So gamma e power s is the point on the geodesic whose chemical distance from the origin is e power s. Okay. So this somehow sort of parameterizes the geodesic in a way so that if you look at some exponentially growing scales, then it sort of spends equal amount of time per scale. Okay, so there is a chat. Oh, sorry, yeah. Yeah, actually, I am usually used to monitoring the chat, but if I don't respond, maybe somebody can point that out to me. Okay. Okay, so this is sort of the parameterization that we'll work with, where a number s goes to the point on the geodesic with distance e power s. And so now, so given this parameterization, so what we will call a typical point is, let's say, sample a point tau uniform between 0 and t. So t is some large number, and just look at the sorry, I don't mean that. So this is a typo. So I mean gamma e power tau. So you look at the geodesic, and the point at which you look at it is e power some uniformly chosen point between 0 and t. Okay. And so just to sort of develop some notations, of field t is going to be this sort of measure, or this sort of random object whose distribution is given by this local field at this randomly chosen point. So recall that gamma e power tau is our typical point between 0 and e power t in some sense. And look at an h bar was our notation for the local field, where we took this ball, scaled everything back to the unit disk, and normalized it to have average 0. So field t is going to be that random object. Okay, so this is, you take this geodesic, you sample some random point, you look at the local field normalized, and that's going to be this random object. And so this lives on the space of distributions. It's actually so D is a space of all smooth functions, and D prime is a space of all continuous linear functionals. So actually, because the Gaussian free field lives on this sort of negative Holder spaces, this object is also living. This object can also be thought of as living in this negative Holder spaces. So this gives you a random measure on this negative Holder space or in the space of continuous linear functionals. Okay, so we don't have to sort of focus too much on that, but I mean, these are spaces on which the Gaussian free field lives, and so naturally this object will also live in the same space. Okay, so given a realization of this Gaussian free field, this object gives you a random measure on these spaces. Okay, and the measure coming from the fact that the source of the measure now is this tau. Right, so everything else is determined. So if I fix the realization of the Gaussian free field, then this random measure, the randomness comes from, so this measure is coming from this measure, the location of the root at which I'm rooting my field. And so the theorem, the main theorem is that these things actually have a limit. So there is a deterministic measure nu, again living in the same space, such that almost surely when you fix a realization of the Gaussian free field H, so almost surely in the realization of H, as t grows to infinity, as you look at a bigger and bigger segment along the geodesic, the field, the random object that you get, this field t, this thing converges in distribution to an object which has this law nu. Okay, so is the statement clear? So there is a deterministic measure nu on this space, so it gives me some sort of distribution, and the point is, if I fix my Gaussian free field and look at this infinite geodesic, and then look at a typical point up to e power t in some sense, so that's some random object, and then that has a law, and the law is only coming from this randomness. Then as t goes to infinity, this sequence of measures actually have a weak limit.
Is there a reason why you restrict to a measure on the disk?
Yeah, so you can make it. So I guess you want it to be on the whole plane, right?
Yeah.
I mean, that's one. So one sort of difficulty that sort of shows up, and I expect this to have the right answer as well. But suppose you have this geodesic, and now the point is, if you sort of take different points, you see that if you take a very large ball, they will all sort of intersect the origin, and somehow some of the arguments actually don't go through as nicely. So I do expect the answer to this to be yes, and you can actually prove a version of this where maybe you do some sort of slight reformulation where you sort of look at the full plane, but maybe minus the unit circle or something, so that you essentially avoid the origin. But for sort of the interesting sort of applications, you only need to sort of realize what exactly is happening very close to the geodesic, and so just looking at some small ball which sort of really focuses on the environment near the geodesic should sort of give you information about how the thing looks like near the geodesic. But yeah, so I expect a version of this result to be true if you look at the entire environment. Yeah.
Also, is it possible to get total variation convergence instead of just convergence and distribution?
So that I don't expect, because somehow you see that if you fix this realization of this Gaussian process, right? So somehow then so the empirical measure is supported on whatever you're seeing on this sort of given realization, right? And so then I think you would actually, if you now sort of take some independent Gaussian free field, then it's not going to actually lie close to this given Gaussian process for any t. And so some of the empirical measures should be all singular with respect to the Gaussian free field noise.
I see. Oh, because you're fixing the realization.
Yeah, because somehow, let's say take a Brownian motion, right? So one-dimensional Brownian motion up to time t, okay? And now let's say you slide a window of size 1.
Yeah.
Along 0 to t. And now you want to ask, like, so for whatever measure on paths that you get, so that will certainly weakly converge to a one-dimensional Brownian motion on 0 to 1, right? But an independent Brownian motion will not lie close to this given realization. So these empirical measures will all be somehow singular to Brownian motion, and so you cannot expect a stronger notion of convergence. Okay. Does that make sense?
Yeah, I see.
Yeah.
Would you have a stronger notion of convergence if you randomized the field?
Oh yeah, so of course, yeah. So if you do some anneal thing, then of course you might expect, because somehow even in this case, right? So if you anneal it, then of course all of these guys are themselves like Brownian motions themselves, right? So if you take the average of this yellow path, then it sort of every segment becomes itself a Brownian motion. And so many things might happen in the anneal setting, which in the coin setting you cannot expect.
Okay. Are you able to prove this anneal?
No, so actually we did not quite pursue that, but certainly the coin statement is not true, and one might be able to sort of prove some version of it for the anneal setting, but yeah, we did not think about it. Other questions?
So is there any difference between you choose a random time or you choose a fixed time? Can you just choose a fixed time and then do the same thing? So here you're choosing it from unit from 0 to t.
So what do you mean? So what is the thing that so what is that goes to infinity though? So what is the sort of the limiting statement? So suppose you have this geodesic.
So just say, so I just have a fixed tau, and then tau goes to infinity. Can you do the same thing? So now you have this tau from this uniform uniformly chosen from 0 to t, right? And then you're sending t to infinity, right?
Yeah. So but like when you say tau.
Yeah. So my question is, can you just say I just choose a fixed tau, and then this is a sequence about tau, and then like tau times infinity. It's basically a difference between.
No, so the point is, like, if you just look at one particular point, right, then of course you will see some weird things along the path. So you cannot expect weak convergence. So you need some averaging to have this.
Oh, I see what you mean. So you want it to be like for every.
You need some averaging to sort of because somehow along the geodesic you will see sort of very weird patterns.
Yeah. Okay.
Yeah.
I see.
Messed up the slide completely, but hopefully it is still readable. So any other questions?
I actually have a somewhat related question. So you're taking this exponential, so you're taking e to the power tau. If you just took tau instead, do you expect the same to be true?
Right. So I'll make a comment about that at the end. Okay. So okay, so we'll see what the broad argument is for this one, and then I'll sort of try to compare it with when you sort of don't do this exponential reparametrization. Yeah.
Okay. Yeah.
Yeah. Okay, so and also in a counterpart sense, we also have convergence of the local metric. So instead of looking at the local field centered at a point, you can also look at, so you can again look at the same thing. You can take a point on the geodesic, you can take some small ball around the geodesic, and now look at the LQG metric restricted to this ball. Okay, again, you want to sort of pull everything back to the unit disk, and then you sort of have this prefactor. So for people who are familiar with it, these things will be sort of very obvious where they come from, but for people who have not seen these things in the past, so these are things that show up because I'm doing this change of variables. So I'm taking the metric from a ball of radius delta times x to a unit disk. So this gives you, and then also have this sort of centering, which made the average 0. And so this is the factor that comes up because of this Weyl scaling, and this is the sort of the change of coordinate formula, how it works in this setting. Okay, so I take this induced metric inside the ball and then and push everything to the unit disk. And so these are continuous functions on the unit disk, cross unit disk. So the metric can be thought of as a continuous function on d cross d. And it turns out, again, you do the same empirical, you can again look at the empirical observable from 0 to e power t tau or something. And in this topology of uniform convergence in compact sets, that's actually uniform on compact sets, on compact subsets. So if you look at this topology, then again, so on the weak convergence under this topology, this empirical measure on metrics converges to a deterministic measure on metrics. Okay, so this is sort of the counterpart result. So the first result was about the local field, and this is about the local metric, and somehow the field and the metric are related. So it's not surprising that this is also true. Okay, so these are sort of the two main limiting results. That if you look along the geodesic and you look at the local field and the local metric, they have the empirical measures converge to some deterministic measures, almost surely in the realization of the underlying field. Okay, so then the question is, how do these things behave corresponding to their typical counterparts, right? So we now have gotten a field which lives on the unit disk whose circle average is 0. And so it turns out, so the typical field is, you'll just simply look at the Gaussian process, the Gaussian free field restricted to the unit disk. And so it turns out that this object that you get as a limit of this empirical measure, this thing is mutually singular with respect to the typical field, the Gaussian free field restricted to the unit disk. Okay. However, all the singularity is coming from near the geodesic. So somehow, if you go slightly away, so this is a unit disk, and suppose you go slightly away from the origin, and you look at this shaded region, and look at the field on the shaded region, then it turns out to be absolutely continuous. So the field that you get restricted to this annulus away from the origin is absolutely continuous to the Gaussian free field counterpart. Okay, so the full thing is singular, but slightly away from the origin becomes absolutely continuous. Again, is the statement clear? Okay. And so I'll describe, so what I have about 10 minutes.
Yeah, you could have a little longer than 10 minutes.
Okay. All right. So I'll try to at least describe some of the key ideas that go into some of the proofs. So one thing that is quite convenient in LPP, this sort of oriented picture that I described, which is absent in FPP, is this issue that the geodesics can backtrack, right? So recall that in LPP, we were simply looking at oriented paths, right? So they were simply going northeast or northwest, which in the sort of limiting sense might look like a simple function that goes up. However, for FPP, there was no such constraint. So the space, so the length minimizing paths can be very strange. It can backtrack. It can do a lot of spiraling behavior. And so that's one of the main issues that people face when they study FPP or LQG, which is also another model of FPP. And so somehow the first step is to sort of somehow control this issue using geodesic coalescence. And so here we sort of use a result again from this paper of Ewan, Josh, and Scott Sheffield, which strengthens an earlier result of Gwen and Miller, which states as following. So maybe the figure is maybe not as nice as I would have liked it to be, but let's say, so you have, let's say, two balls, one with unit radius, another ball. So let's say both of them are centered at the origin. So this is the origin. So you have two balls, one centered at the one with unit radius, the other one has radius epsilon. And so the statement is that if you take any point inside this ball of radius epsilon, and you look at any point outside the ball of radius 1, and if we look at the geodesics, they all sort of merge. So there is a common point Z, which is shared by all the geodesics which start from inside this smaller ball and ends outside this bigger ball. Okay, with high probability. So if epsilon is very small, then with 99% chance, every geodesic starting from inside this ball and ending outside this ball will meet and share a common point. So they all sort of coalesce. Okay. Is the statement of this coalescence picture clear? Okay. And so using that, actually, you can give some sort of a notion of directedness to the geodesic, which a priori can have a lot of backtracking. So, so again, this picture, so this previous statement is scale invariant. So instead of doing epsilon and 1, you can do, let's say, 1 and a billion, or a very, very large number, k. So again, this picture will be the same because of scale invariance. And so using that, you can divide your space into some exponentially growing scales, let's say with the scaling factor being k, where k is some large number. And so then what will happen is that you will sort of see this annuli from k to the I to k to the I plus 1 and so on. And with positive probability for each annuli, you will have a picture like this, where if you look at any geodesic which goes from the inner boundary to the outer boundary, they will all coalesce. And it's essentially a restatement of what I just said here for the ball. So think of this epsilon ball being the inner radius, and the boundary of this epsilon ball being the inner radius, and the boundary of the radius 1 ball being the outer radius. Okay, so it might not happen at every scale, but it will happen with constant chance at any given scale. This picture will be true with constant chance. Okay, but now the point is, once you have this coalescence picture in one scale, then from then on you will not backtrack again, right? So it will not happen that, suppose you have a coalescence picture here, then it will not happen. So something like this will not happen. Okay. And so this sort of gives you some sort of notion of directedness, where there might be some very local spiraling behavior, but between these two sort of, between these coalescence points that you sort of witness across different scales, it somehow sort of proceeds in sort of a directed fashion. Okay, and that's sort of the thing that allows us to have this sort of notion of directedness in the geodesic by sort of witnessing these points of coalescence. Okay. And so in the previous picture, this PIs were these points of coalescence. And if you look at this infinite geodesic, and now you look at the segments between P0 and P, sorry. Yeah. So if you look at this segments between the consecutive coalescence points, that gives you some sort of a renewal structure to your geodesic. And again, because of scale invariance, these locally look exactly the same up to the scaling. Okay, so the geodesic now has this sort of renewal structure, and we want to prove some thing converges along the geodesic. So it's sort of natural to sort of invoke some law of large numbers type statement. Okay, so that's exactly what we'll do. However, to do that, you need some decay of correlation, right? So suppose you have some stationary sequence, which is which has some sort of a renewal structure, and then so not stationary, but some sort of a renewal sequence. But then to sort of say that you have some law of large numbers, you need to say that there is some rough independence in this along the sequence. And this is where sort of the domain Markov property comes in. So the space-time white noise in this sort of classical setting of FPP or LPP that I described automatically has this inbuilt independence in it. So that gets replaced by the domain Markov property in sort of the LQG setting, where because the underlying field, the Gaussian free field, has this property, and that is what we will expect to get this decay of correlation. Okay, so again, this is sort of a technical slide. I don't want to spend too much time on this, but again, you do this sort of exponential decomposition of your space, and again, so you look at, let's say, for any I, you look at the field. So let's say this is k to the I. So you look at this field from here onwards, from k to the I to infinity. Okay, so now you sort of center it so that the average on this circle becomes 0. So average on this circle, average on the boundary of this region becomes 0. So that's something that we denote as h hat k to the I. And then let's say capital uppercase hi is simply that thing scaled back to c bigger than 1. So instead of having the field living on k to the I onwards, we scale everything back so that it lives from the radius 1 onwards. Okay, so for every I, you take this field from k to the I onwards and scale it back so that they'll all live on the same space, which is the complex plane minus the unit disk. Okay, and so again, by conformal invariance of this Gaussian free field, and this is sort of the precise statement of conformal invariance. We are using a very particular sort of application of that where we are only sort of scaling it. So it's more like a scale invariance. It turns out that these fields that I just constructed that all live on this complex plane minus the disk domain, they form a stationary sequence. For every k to the I, the field from k to the I onwards properly scaled back forms a stationary sequence. And this is the key lemma that it actually exhibits some exponential decay of correlation. So suppose I give you all the information up to k to the I, then the field, then the conditional law from k to the j onwards, properly scaled, has a very so the Radon-Nikodym derivative of the conditional law to the unconditional law is very close to 1 in an L2 sense, and this closeness is exponentially decaying as a function of the distance between j and I. Okay. Again, the precise statements are not super important. The whole point is that the domain Markov property and some estimates of how the boundary behaves sort of allows us to prove that the fields on this different sort of annuli are almost independent. I mean, they exhibit an exponential decay of correlation. Okay, so now we have this geodesic, which has this Renewal structure, Renewal type structure because of this sort of coalescence points. And this sort of coalescence points are things that happen in different annuli of different growing scales. And we also show that the sort of the noise in this different annuli have exponential decay of correlation. So we are in good shape to sort of invoke law of large numbers type statements. Okay, so one more thing though, and I think I'll probably, because I'm running out of time, I'll probably skip this slide. So this sort of, we also have to remember that we have this log parametrization, and that's not a local thing, right? So somehow, so we have this geodesic, and you have this different annuli, and because of this log parametrization, the log parametrization in this part of the geodesic, let's say, is not simply a function of the noise here, because somehow the log sort of takes into account the information about the past as well. But that's something that you can also handle using sort of this renewal structure. It turns out that there is sort of a very nice description of this log parametrization using the fact that the radial part of the Gaussian free field is a Brownian motion. And okay, so I am running out of time, so I won't sort of spend much time on this, but I'm happy to sort of discuss this point offline. But okay, so the renewal structure is there. There's exponential decay of correlation. The renewal structure can also be sort of seen in this log parametrization using sort of properties of the Gaussian free field. And so this allows us to use law of large numbers for renewal processes, for stationary processes with exponential decay of correlation to get the main results. Okay, so that's sort of the upshot. Okay, so I'm sort of almost out of time, so I'll try to at least sort of give some quick arguments of the remaining results about this sort of mutual singularity and the absolute continuity of the field with respect to its typical counterpart. Okay, so first, mutual singularity. So why is the field mutually singular? So you see that this is the picture, right? So we have this geodesic, and we are sitting on a point on the geodesic, and we are looking at the environment from that point. So of course, it's because of the way we have set up this scenario, this field has a property that there is a geodesic passing through the origin, right? Because of how we have sort of moved our environment around. So this field that we see from the geodesic has a property that there is a local geodesic which passes through the origin from one point on the boundary to another. And this actually does not ever happen in the typical setting. And so this is related to this sort of non-existence of a bigeodesic. So for people who are, as the name sort of indicates, a bigeodesic is a bi-infinite path, such that every segment is a geodesic. Every finite segment is a geodesic. And so it was shown in this paper of Ewan, Josh, and Scott that in LQG, there is no bigeodesic passing to the origin. There is no bigeodesic period. In particular, there is no bigeodesic passing to the origin. And this existence, non-existence of bigeodesic is actually a very important problem as well. And it's sort of currently open for FPP in Z2. And this was originally posed by Furstenberg. And so very recently, it has been rolled out for LPP by two groups of authors, one being Basu, Hoffman, and Sly, and the other one being Timo Sepalainen, and I don't remember the other authors, unfortunately. Yeah, but for LQG, it has been ruled out that you do not actually have any bi-infinite path passing through the origin, which is a geodesic. And you see that that's sort of the, and the main reason is the following, roughly, is that you will always have this. So if you look at sort of scales converging to the origin, you will always have shortcuts that are significantly better. So it sort of incentivizes the path to take this shortcut instead of actually passing to the origin. So that's really the main reason. So you will have infinitely many chances of taking this shortcut than going across. And so eventually will not actually go through the origin. That's sort of the broad intuition. You can also use geodesic coalescence to sort of argue this. Okay. So, but the upshot is that you do not have any sort of bi-infinite path or any sort of path which is a geodesic which passes to the origin. However, for the field that we get by routing the environment at the origin, by definition, there is one. And so that's why you don't expect them to be absolutely continuous. So a technical point is that this sort of issue of the geodesic and whatnot is a statement about the metric. However, we were claiming things about the field. We said that the field is singular to the Gaussian free field. However, this sort of notion of geodesics is a property of the metric. But as I said, so it turns out that this sort of metric can be realized as a function of the field. So there actually is a measurable function between the right spaces, so that if you look at the LQG metric on the unit disk, that's the function evaluated at the Gaussian free field on the unit disk. And similarly, the same function evaluated on the field that you get as the limit of this empirical measure will give you the metric that you get as the limit of this empirical measures. Okay, so there is a coupling of this limiting objects so that you get one of them by evaluating this function at the other object. Okay, so statement about singularity of the metric can be used to prove statement about singularity of the underlying fields. Okay, so that's the statement about singularity, and so I'll sort of just one slide about how to prove absolute continuity. And so this will be a bit quick, so it might not be super clear, but so I'll sort of at least sort of make a quick attempt. So the basic idea is so you have this red geodesic. So what we'll do is try to at least sort of predict a sort of So what I'll do is I'll try to predict segments of the red geodesic using local information. So let's say I have some rational point Q, and I take two balls of radius epsilon1 and epsilon2, and these are all rationals. And so I look at all geodesics between rational points inside this ball of radius epsilon2, and look at the intersection with the inner ball. So you can sort of show that on the event that the geodesic actually intersects this ball. If it intersects the smaller ball, the intersection should agree with subsegments of this local geodesics. So this global geodesic will overlap with this local geodesics inside this smaller ball. So which means that we don't know whether this global geodesic actually enters this ball or not. But if it were to enter, then its intersection must be a subset of this local geodesics. Okay, so this allows us to predict what this local segments of the geodesic look like. And now, but the point is, this local geodesics crucial are only a function of this local noise. And if this ball is very small, you see that as you go away from the origin, you have not revealed anything about this noise here. And this is still sort of absolutely continuous with respect to the GFF. So somehow that's sort of the key idea, that you can sort of predict the local small segments on the geodesic by revealing very tiny information. And because you're interested in balls of radio, so because you're interested in the noise slightly away from the geodesic, you can sort of predict these segments without revealing any noise here. And so that's why you still sort of preserve absolute continuity slightly away from the geodesic. And then you can take union bound over all rational balls with rational radii and things like that to make this precise. But that's sort of the broad idea, that because you're going slightly away from the geodesic and you can predict local segments of the geodesic by very tiny local information using geodesic coalescence, you have not revealed anything here, and conditional on everything here by domain Markov, the noise here is still absolutely continuous. So that's sort of the basic idea going into the proof of absolute continuity. And I'll just sort of end with one open problem. So what is sort of the description of the singularity? So we know this field is singular with respect to the GFF. And so somehow the basic intuition is that because this geodesic is length minimizing, it should pass through atypically small values. And so so this question is in some sense a metric version of the following statement that was already proven in this sort of famous work of Sheffield and Duplantier on the Liouville measure. So if you take a gamma-Liouville measure and you take a random sample from that, almost surely it's a gamma thick point. And for people who are not familiar with that, it essentially says that locally the Gaussian free field is much higher than typical, and this is the precise way to make sense of it. You take local averages and then you do an appropriate limit. Okay, so somehow the point is, what is sort of the thickness of a point on the geodesic is sort of the rough, is sort of related to this question, and what the source of the singularity is. So I'll stop here, and I'm happy to answer questions and discuss more. So Nina asked a question which I'll talk about, but if there are other questions, I'm happy to answer them as well.